Hello friends, welcome to the channel NCERT Audiobooks. Today we are going to read chapter 12 of the book that is Certificate Physical and Human Geography written by G.C. Leong. Before starting the chapter, I would like to tell you that we have uploaded all the chapters on our channel. You can go and check it out. So let us start. Chapter 12, The Oceans. Exploring the Oceans. The oceans, comprising more than 70% or 140 million square miles of the Earth's surface, have tremendous potential waiting to be developed. Besides being a source of food, fish, mammals, reptiles, salt, and other marine foodstuffs, the tides can be harnessed to provide power. Formal oceanographic investigation began only with the British expedition of the Challenger 1873 to 1876, the first successful worldwide deep sea expedition. Oceanography. The science of the oceans has become such an important subject in recent years that researches into the deep seas have been conducted by many institutions, universities, government ministries, and other international organizations. The most famous international oceanographic research center is the International Council for the Exploration of the Sea with its headquarters in Copenhagen. Ocean exploration for the observation and recording of oceanographic data is a very expensive matter. It involves the operation and maintenance of specially equipped vessels in mid-ocean for long periods, and large-scale oceanographic researches are thus best undertaken by international bodies. The old echo sounding techniques have now been replaced by radar sounding and electrical echo devices to find the precise depths of ocean floors and map the relief of the oceans. Trained frogmen equipped with modern breathing apparatus are employed to gather valuable information from great depths. Deep sea core samples are obtained by boring for the study of the oceanic deposits. The various kinds of oozes, muds, and clays. Automatic recording thermometers and other sensitive instruments can be lowered to any required depth by stationary vessels, with laboratory facilities for processing any required data. For the observation and measurement of current flow, various kinds of current meters using propellers, vanes, or pendulums have been designed. Sealed bottles and other floating objects containing instructions for reporting their precise time and place of discovery are released in large numbers to compute with rate and direction of drift and current flow. With all these modern techniques at the disposal of the oceanographers, our knowledge of the mysteries of the oceans is greatly increased, but there is still much to be discovered. Now we are going to read the relief of the ocean. The ocean basins are in many ways similar to the land surface. There are submarine ridges, plateaux, canyons, plains, and trenches. A section drawn across an ocean illustrates the typical submarine relief features. And the first one is Continental Shelf. This is in fact the seaward extension of the continent from the shoreline to the continental edge, marked approximately by the 100 fathom 600 feet isobar. Isobars are contours marking depths below sea level. The continental shelf is thus a shallow platform whose width varies greatly from a few miles in the North Pacific of the continent of North America to over 100 miles off northwest Europe. In some places where the coasts are extremely mountainous, such as the Rocky Mountain and the Andean coasts, the continental shelf may be entirely absent. Of broad lowland coasts like those of Arctic Siberia, a maximum width of 750 miles has been recorded. A width of 20 to 100 miles is generally encountered. The angle of the slope is also variable and is normally least where the continental shelf is widest. A gradient of 1 in 500 is common to most continental shelves. Many regard the continental shelf as part of the continent submerged due to a rise in sea level. Example, at the close of the ice age, when the ice in the temperate latitudes melted and raised the sea level by several hundred feet, some smaller continental shelves could have been caused by wave erosion where the land is being eroded by the sea, as shown in figure 93. Conversely, such shelves might have been formed by the deposition of land derived or river borne materials on the offshore terrace, as in figure. The continental shelves are of great geographical significance for the following regions. The first one is their shallowness enables sunlight to penetrate through the water, which encourages the growth of minute plants and other microscopic organisms. They are thus rich in plankton on which millions of surface and bottom feeding fishes thrive. The continental shelves are therefore the richest fishing grounds in the world. Example, the Grand Banks of Newfoundland, the North Sea, and the Sunda Shelf. The second one is their limited depth and gentle slope keep out cold undercurrents and increase the height of tides. This sometimes hinders shipping and other marine activities since ships can only enter and leave port on the tide. Most of the world's greatest seaports, including Southampton, London, Hamburg, Rotterdam, Hong Kong, and Singapore, are located on continental shelves. The second one is the continental slope. At the edge of the continental shelf, there is an abrupt change of gradient to about 1 in 20, forming the continental slope. The third one is the deep sea plain. This is the undulating plain lying 2 to 3 miles below sea level and covering two-thirds of the ocean floor, generally termed the abyssal plain. It was once thought to be featureless, but modern sounding devices reveal that the abyssal plain is far from being level. It has extensive submarine plateaux, ridges, trenches, basins, and oceanic islands that rise above sea level in the midst of oceans. Example, the Azores, Ascension Island. The fourth one is the ocean deeps. These are the long, narrow trenches that plunge as great ocean deeps to a depth of 5,000 fathoms or 30,000 feet. Contrary to our expectations, most of the deepest trenches are not located in the midst of oceans. They are more often found close to the continents, particularly in the Pacific Ocean, where several deep trenches have been sounded. The greatest known ocean deep is the Mariana Trench near Guam Island, which is more than 36,000 feet deep. We can see from this that ocean trenches are greater in magnitude than the highest mountains on land, for the highest peak, Mount Everest, is only 29,028 feet. Other notable ocean deeps include the Mindanao Deep, that is 35,000 feet, the Tonga Trench, 31,000 feet, and the Japanese Trench, 28,000 feet, all in the Pacific Ocean. Now we are going to read the oceanic deposits of the ocean floor. Materials eroded from the earth, which are not deposited by rivers or at the coast, are eventually dropped on the ocean floor. The dominant process is slow sedimentation, where the eroded particles very slowly filter through the ocean water and settle upon one another in layers. The thickness of the layer of sediments is still unknown. Its rate of accumulation is equally uncertain. Generally speaking, we may classify all the oceanic deposits as either muds, oozes, or clays. The first one is the muds. These are terraneous deposits because they are derived from land and are mainly deposited on the continental shelves. The muds are referred to as blue, green, or red muds. Their coloring depends upon their chemical content. The second one is the oozes. These are pelagic deposits because they are derived from the oceans. They are made of the shelly and skeletal remains of the marine microorganisms with calcareous or silicaceous parts. Oozes have a very fine floor-like texture and either occur as accumulated deposits or float about in suspension. The third one is the clays. These occur mainly as red clays in the deeper parts of the ocean basins and are particularly abundant in the Pacific Ocean. Red clay is believed to be an accumulation of volcanic dust blown out from volcanoes during volcanic eruptions. Now we are going to read the salinity of the ocean. Almost every known chemical element can be found in varying proportions in the oceans, whose most characteristic feature is their salinity. In contrast to the fresh water of lakes and streams, all seawater contains large amounts of dissolved mineral matter, of which sodium chloride or common salt alone constitutes more than 77%. The other more important compounds include magnesium, calcium, and potassium, while the rest are distinguishable only in traces of very minute quantities. Due to the free movement of ocean water, the proportions of different salts remain remarkably constant in all oceans and even to great depths. But the degree of concentration of the salt solution in ocean does vary appreciably in different areas. This is expressed as salinity, the degree of saltness of water, either as a percentage or more often in parts per thousand. Variations are shown in salinity distribution maps by isohalines, lines joining places having an equal degree of salinity. Generally speaking, the average salinity of the oceans is 35.2 degree, about 35 parts of salt in 1000 parts of water. In the Baltic Sea, where there is much dilution by fresh water and melting ice, the salinity is much lower, only about 7%. In the Red Sea, where there is much surface evaporation and fewer rivers to bring in fresh water, the average salinity increases to 39. In enclosed seas, which are areas of inland drainage such as the Caspian Sea, the salinity is very high, 180, and in the Dead Sea of Palestine, a salinity of 250 has been recorded. The highest salinity is perhaps that of Lake Van in Asia Minor with 330. It is a salt lake and salts are collected from its shores. The density of the water is so high that in Lake Van or the Dead Sea it is almost impossible to sink. Beginner swimmers will find it much easier to float here than anywhere else. The variation of salinity in the various seas and oceans is affected by the following factors. The first one is the rate of evaporation. The waters fringing the high pressure belts of the trade wind deserts between 20° and 30° north and south have high salinity because of the high rate of evaporation caused by high temperature and low humidity. The temperate oceans have lower salinity due to the lower temperature and a lower rate of evaporation. The second one is the amount of fresh water added by precipitation, streams, and icebergs. Salinity is lower than average 35 in equatorial waters because of the heavy daily rainfall and high relative humidity. Oceans, into which huge rivers like the Amazon, Congo, Ganges, Irrawaddy, and Mekong drain, have much of their saltness diluted and have a lower salinity. The Baltic, Arctic, and Antarctic waters have a salinity of less than 32 because of the colder climate with little evaporation and because much fresh water is added from the melting of icebergs, as well as by several large poleward bound rivers, example Ob, Lena, Yenisei, and Mackenzie. The third one is the degree of water mixing by currents. In wholly or partially enclosed seas such as the Caspian Sea, Mediterranean Sea, Red Sea, and Persian Gulf, the waters do not mix freely with the ocean water and they are not penetrated by ocean currents. Salinity is high, often over 37. In areas of inland drainage without links with the oceans, continuous evaporation under an almost cloudless sky causes the accumulation of salts around the shores. In the open oceans where currents freely flow, salinity tends to be near the average 35 or even a little lower. The range of salinity is negligible where there is free mixing of water by surface and subsurface currents. Now we are going to read the temperature of ocean water. Like land masses, ocean water varies in temperature from place to place, both at the surface and at great depths. Since water warms up and cools down much more slowly than the land, the annual range of temperature in any part of the ocean is very much smaller. It is less than 10° Fahrenheit for most of the open seas. Generally, the mean annual temperature of the surface ocean water decreases from about 70° Fahrenheit in the equatorial areas to 55° Fahrenheit at latitudes 45° north and south, and drops almost to freezing point at the poles. The reduction of temperature with latitude is, however, never constant because of the interference by warm and cold currents, winds, and air masses. Unlike the solid earth, ocean water is mobile and variations in the temperature between different parts of the oceans can be expected. Water flowing out from the Arctic and Antarctic as cold currents, such as the Labrador Current of northeast Canada, tends to reduce the surface water temperature. Ports of eastern Canada, even at 45 degrees north, are thus icebound for almost half the year. In the same way, coasts warmed by warm currents such as the North Atlantic Drift have their surface temperature raised. The Norwegian coast, even at latitudes 60 to 70 north, is ice free throughout the year. The highest water temperatures are found in enclosed seas in the tropics. Example, the Red Sea, which records a temperature of 85 to 100 Fahrenheit. The Arctic and Antarctic waters are so cold that their surface is permanently frozen as pack ice down to a depth of several feet. In the warmer summer, parts of the ice break off as icebergs that both dilute the water and lower the surface temperature of surrounding ice free seas. The temperature of the oceans also varies vertically with increasing depth. It decreases rapidly for the first 200 fathoms at the rate of 1 degree Fahrenheit for every 10 fathoms, and then more slowly until a depth of 500 fathoms is reached. Beyond this, the drop is scarcely noticeable, less than 1 degree Fahrenheit for every 100 fathoms. In the ocean deeps below 2000 fathoms, that is 12,000 feet, the water is uniformly cold, just a little above freezing point. It is interesting to note that even in the deepest ocean trenches, more than 6 miles below the surface, the water never freezes. It is estimated that over 80% of all ocean waters have a temperature between 35 and 40 Fahrenheit. Now we are going to read the movements of ocean currents. Ocean currents are large masses of surface water that circulate in regular patterns around the oceans, as shown in the world map. Those that flow from equatorial regions polewards have a higher surface temperature and are warm currents. Those that flow from polar regions equatorwards have a lower surface temperature and are cold currents. Their direction of movement is indicated by the arrows. But why should they follow such a pattern? Some of the underlying factors are explained below. The first one is the planetary winds. Between the equator and the tropics blow the trade winds, which move equatorial waters polewards and westwards and warm the eastern coasts of continents. For example, the northeast trade winds move the north equatorial current and its derivatives, the Florida current and the Gulf Stream drift to warm the southern and eastern coasts of USA. Similarly, the southeast trade winds drive the south equatorial current which warms the eastern coast of Brazil as the warm Brazilian current. In the temperate latitudes blow the westerlies. Though they are less reliable than the trade winds, they result in a northeasterly flow of water in the northern hemisphere so that the warm Gulf Stream is driven to the western coast of Europe as the North Atlantic Drift. In a similar manner, the westerlies of the southern hemisphere drive the west wind drift equatorwards as the Peruvian Current of South America and the Benguela Current of Southern Africa. The planetary winds are probably the dominant influence on the flow of ocean currents. The strongest evidence of prevailing winds on current flows is seen in the North Indian Ocean. Here the direction of the currents changes completely with the direction of the monsoon winds which come from the northeast in winter and southwest in summer. The second one is temperatures. There is much difference in the temperature of ocean waters at the equator and at the poles. As warm water is lighter and rises and cold water is denser and sinks, warm equatorial waters move slowly along the surface polewards, while the heavier cold waters of the polar regions creep slowly along the bottom of the sea equatorwards. The third one is salinity. The salinity of ocean water varies from place to place. Waters of high salinity are denser than waters of low salinity. Hence, waters of low salinity flow on the surface of waters of high salinity, while waters of high salinity flow at the bottom towards waters of low salinity. For example, in the Mediterranean region, there is a great difference in salinity between the waters of the open Atlantic and those of the partially enclosed Mediterranean Sea. The less saline water of the Atlantic flows on the surface into the Mediterranean, and this is compensated for by an outflow of denser bottom water from the Mediterranean. The fourth one is the Earth's rotation. The Earth's rotation deflects freely moving objects, including ocean currents, to the right. In the northern hemisphere, this is a clockwise direction. Example, the circulation of the Gulf Stream drift and the Canaries current. In the southern hemisphere, it is an anti-clockwise direction. Example, the Brazilian current and the west wind drift. The fifth one is land. A land mass always obstructs and diverts a current. For instance, the tip of southern Chile diverts part of the west wind drift northwards as the Peruvian current. Similarly, the shoulder of Brazil at Cape Sao Roque divides the west flowing equatorial currents into the Oceanic current, which flows northwestwards, and the Brazilian current, which flows southwestwards. Now we are going to read the circulation of the Atlantic Ocean. We shall begin with the north and south equatorial current at the equator. The steady trade winds constantly drift two streams of water from east to west. At the shoulder of the northeast Brazil, the protruding land mass splits the south equatorial current into the Oceanic current, which flows along the Guiana coast, and the Brazilian current, which flows southwards along the east coast of Brazil. In the North Atlantic Ocean, the Oceanic current is joined and reinforced by the North Equatorial Current and heads northwestwards as a large mass of equatorial water into the Caribbean Sea. Part of the current enters the Gulf of Mexico and emerges from the Florida Strait between Florida and Cuba as the Florida Current. The rest of the equatorial water flows northwards east of the Antilles to join the Gulf Stream of the southeastern USA. The Gulf Stream drift is one of the strongest ocean currents, 35 to 100 miles wide, 2,000 feet deep, and with a velocity of 3 miles an hour. The current hugs the coast of America as far as Cape Hatteras, latitude 35° north, where it is deflected eastwards under the combined influence of the westerlies and the rotation of the earth. It reaches Europe at the North Atlantic drift. This current, flowing at 10 miles per day, carries the warm equatorial water for over 1,000 miles to the coasts of Europe. From the North Atlantic, it fans out in three directions: eastwards to Britain, northwards to the Arctic, and southwards along the Iberian coast as the cool Canaries current. Oceanographic researches show that almost two-thirds of the water brought by the Gulf Stream to the Arctic regions is returned annually to the tropical latitudes by dense, cold polar water that creeps southwards in the ocean depths. The Canaries current, flowing southwards, eventually merges with the North Equatorial Current, completing the clockwise circuit in the North Atlantic Ocean. Within this ring of currents, an area in the middle of the Atlantic has no perceptible current. A large amount of floating seaweed gathers, and the area is called the Sargasso Sea. Apart from the clockwise circulation of the currents, there are also currents that enter the North Atlantic from the Arctic regions. These cold waters are blown south by the outflowing polar winds. The Ermingan current, or the East Greenland current, flows between Iceland and Greenland and cools the North Atlantic drift at the point of convergence. The cold Labrador current drifts southeastwards between West Greenland and Baffin Island to meet the warm Gulf Stream of Newfoundland as far as south as 50° north, where the icebergs carried south by the Labrador current melt. The South Atlantic Ocean follows the same pattern of circulation as the North Atlantic Ocean. The major differences are that the circuit is anti-clockwise and the collection of seaweed in the still waters of the mid-South Atlantic is not so distinctive. Where the South Equatorial Current is split at Cape Sao Roque, one branch turns south as the warm Brazilian Current. Its deep blue waters are easily distinguishable from the yellow, muddy waters carried hundreds of miles out to sea by the Amazon further north. At about 40° south, the influence of the prevailing westerlies and the rotation of the earth propel the current eastwards to merge with the cold west wind drift as the South Atlantic Current. On reaching the west coast of Africa, the current is diverted northwest as the the cold Benguela Current, the counterpart of the Canarese Current. It brings the cold polar waters of the west wind drift into the tropical latitudes, driven by the regular southeast trade winds. The Benguela Current surges equatorwards in a northwesterly direction to join the south equatorial current. This completes the circulation of the currents in the South Atlantic. Between the north and south equatorial currents is the east flowing equatorial counter current. Now we are going to read the circulation of the Pacific Ocean. The pattern of circulation in the Pacific is similar to that of the Atlantic, except in modifications which can be expected from the greater size and the more open nature of the Pacific. The circulation can be easily followed in figure. Try to correlate it with the currents in the Atlantic. The North Equatorial Current flows westwards with a compensating equatorial counter current running in the opposite direction. Due to the greater expanse of the Pacific and the absence of an obstructing land mass, the volume of water is very much greater than that of the Atlantic Equatorial Current. The northeast trade winds blow the North Equatorial Current off the coast of the Philippines and Formosa into the East China Sea as the Kuroshio or Japan Current. Its warm waters are carried polewards as the North Pacific Drift, keeping the ports of the Alaskan coast ice-free in winter. The cold Bering Current or Alaskan Current creeps southwards from the narrow Bering Strait and is joined by the Okhotsk Current to meet the warm Japan Current as the Oahu of Hokkaido. The cold water eventually sinks beneath the warmer waters of the North Pacific Drift. Part of it drifts eastwards as the cool Californian Current along the coast of the western USA and coalesces with the North Equatorial Current to complete the clockwise circulation. The current system of the South Pacific is the same as that of the South Atlantic. The South Equatorial Current, driven by the southeast trade winds, flows southwards along the coast of Queensland as the East Australian Current, bringing warm equatorial waters into temperate waters. The current turns eastwards towards New Zealand under the full force of the westerlies in the Tasman Sea and merges with part of the cold west wind drift as the South Pacific Current. Obstructed by the tip of southern Chile, the current turns northwards along the western coast of South America as the cold Humboldt or Peruvian Current. The cold water chills any wind that blows on shore so that the Chilean and Peruvian coasts are practically rainless. The region is rich in microscopic marine plants and animals that attract huge shoals of fish. Consequently, millions of seabirds gather here to feed on the fish. Their droppings completely whiten the coastal cliffs and islands, forming thick deposits of guano, a valuable source of fertilizer. The Peruvian Current eventually links up with the South Equatorial Current and completes the cycle of currents in the South Pacific. Now we are going to read the Indian Ocean circulation. As in the other oceans as illustrated in the figure, the currents of the South Indian Ocean form a circuit. The Equatorial Current turning southwards past Madagascar as the Agulhas or Mozambique Current merges with the west wind drift, flowing eastwards and turns equatorwards as the West Australian Current. In the North Indian Ocean, there is a complete reversal of the direction of currents between summer and winter due to the changes of monsoon winds in summer from June to October, when the dominant wind is the southwest monsoon. The currents are blown from a southwesterly direction as the southwest monsoon drift. This is reversed in winter beginning from December, when the northeast monsoon blows the currents from the northeast as the northeast monsoon drift. The currents of the North Indian Ocean demonstrate most convincingly the dominant effects of winds on the circulation of ocean currents. With this, our chapter ends. Until then, subscribe our channel, listen to the audiobooks, and study well. Thank you.